On to problem number 4. We have the question, the reaction shown has the activation energy of 350 kilojoules per mole, and the activation energy of the reverse reaction is 260 kilojoules per mole. Estimate delta H in kilojoules per mole for the reaction as written. Okay, we can go about this really easy and finish it in a second if we just went about using this equation, where delta H, or enthalpy, is the same as the forward activation energy minus the reverse activation energy. And that would give us right away our answer to be B, because 350 minus 260 is 90. Understanding the concept behind it can also be important as well if we were ever given a problem that wanted us to identify or draw out an activation energy. So knowing whether it's exothermic, like the problem shown below on the left, this right here is exo, and the one on the right is endo. You can tell this by looking at our products to reactants. This is exo because the energy leaves. Our product had more energy than our reactant. This, on the vertical, you have energy, so more energy as you go up. Since more energies were in the products than the reactants, some had to leave, so it exited. It's exothermic. And then on the right, we have products having low energy on the low energy scale, and reactants having more. So here you stored energy, you put it inside the molecule, so it's endo. Okay. Knowing that, we now have to be able to tell the activation energies. So which one of these would have a higher activation energy? This activation energy, because it's exothermic, you start activation energy from where the product line starts. So it goes up here into the top of the activation energy hill. This is the energy of the transition state. We use that symbol for the transition state. And if we did that same thing, started the line by where the products are on an endothermic, you have to go a lot higher up on this hill. So endothermic reactions have high activation energies in the forward, when going forward, and then when going backward. So let's say we had to do this for the reverse, and we said that now this side was the product instead of the reactant, and this side was the reactant instead of the product. We would draw the line down over here, because that's the product, and we draw the activation energy here. So it'd be a lot lower. So endo, going forward, has high activation energy, and backward, because it comes exergonic, you really flip this and you end up with this exergonic you end up with the exergonic reaction over here. That's all you do. So you end up with high activation energy going forward because it's endergonic, and when you go backward, it's exergonic, so it has lower activation energy. So that again shows us we started off with a high activation energy and got a low one. So this is an endergonic reaction. So that tells us if we wanted to draw the activation curve, we would draw this one on the right. And enthalpy, or delta H, is the difference between the energy of the product and the reaction. And as we said before, endergonic ones have much more energy in the product. That's the energy stored, and it's positive when it's endergonic, because you're storing that energy away. So again, it tells us again that it's B. If it was exergonic, or negative here, it would have a huge loss. So you'd lose energy, like we said exergonic does.